I'm going to go ahead and let people in, Tomas.
Okay, if you like, yeah. You can say that I'm abroad.
Okay.
Am I locked in my car? I don't know. It's not, but it's bad and then somewhere nice, but then it's not great.
Sure.
It will be. Settings.
All right. Should we get started, Dr. Ross?
Sure.
So welcome everyone to this is an eager live stream. We're privileged to have joining us from his time abroad. We'll see. Yeah, which means that the internet is going to be interesting. But we're going to do an interview today. Dr. Tomas Ross is a neuroscientist and researcher in Zurich, and he's going to talk today about the course.
University of Geneva, actually.
University of Geneva, my bad.
Yeah, it's okay.
I'm from Florida. That's my excuse for just being terrible at geography. We're going to talk today about what the course that's coming up in several weeks on the neuroscience of neurofeedback. And in particular, what we've been talking about and what the course is going to be about is how, first, why it's important to understand the neuroscience that really forms a foundation for neurofeedback. And then also how neurofeedback works as it's understood by emerging neuroscience. Welcome, Dr. Ross. Would you like to say a couple of words about what your interest in this topic in general is, and why you think it's important for people to learn it?
Sure. I mean, hello everybody. Thanks for coming to this live stream, and also apologies for the setting, but it's the most sound isolated part that I could find, also with an internet connection. It's my Tesla, and I'm currently in Slovenia, so it's I'm on a summer holiday, but we couldn't change this live stream date. So anyway, I'm happy to talk to you a little bit about the course and talk about a bit, my background in neuroscience, as well as why I think it's important to have a neuroscientific approach to neurofeedback. I mean, obviously, there's the word neuro in neurofeedback, so we can't really underestimate how much it's important to know more about the brain in applying neurofeedback. And I think it's critical that essentially things are seen from the point of view of the brain. I know there's a lot of models about how neurofeedback works, and there's some psychological theories and also operant conditioning. And all of these, I think, can be accommodated within the neuroscience framework. But I think also neuroscience, as much as it's complex, it can also simplify things, so people can understand how neurofeedback maybe works from the point of view of the neuronal activities and how they're connected. So all these things that we've learned through neuroscience about plasticity and the link between these brain oscillations and brain waves and behavior. Also, there's quite a lot of theories now on complex systems in terms of how the brain might work, in terms of how it's connected order and disorder, entropy, different things like that, that could illuminate the mechanisms of why neurofeedback in some sense works, because it seems like a magic technique, right? It has apparently some amazing effects, and I've seen them myself. So it's I don't think there's any, there's no real consensus at the moment about how exactly it works, but I think there's some frameworks in neuroscience that I think are getting closer to explaining why it might work as well as it works, and also about plasticity and so on, which it's a radical departure from the usual ways of treating the brain, like medications, for example. So I would like to give a course about how this differs and how they can be still accommodated within the framework of what we know about the brain so far. Yeah.
Great. I wonder if you could talk a little bit. You have a rather diverse sort of journey. The way that you've gotten to where you are doing neuroscience at the University of Geneva. Because you've studied a bunch of different things. You're really approaching this from kind of an interdisciplinary lens. I wonder if you could talk a little bit about what your educational background is and how that brings you to this topic.
Sure, yeah. I mean, I have a background, my bachelor was first in physics. So there I sort of looked at a lot of different things in physics, but then in some sense I kind of started to, we had a course on biophysics of nerve cells, and that kind of attracted me to the brain. And I'm always interested also in like the humanities and psychology. So I thought that would be a nice, started to kind of start to bridge across a little bit from pure, maths and science from physics point of view to more like this neuroscience. Then I did a master's in neuroscience in France. And then after that, I came back to London and I met Jon Griselier, who was at that time, had his own group doing neurofeedback in London. So one of the few groups that was active in kind of neurofeedback, 𝗔𝗂𝗏 neurofeedback research in Europe. And so I was quite interested in this sort of technique, but at that point it was more like a sort of, using brain signatures to control different video games. And at the point when it was apparent that you could use it for treating sort of brain disorders, that's when it got really interesting for me. And I think at that time also there was not that many theories. There were a lot of, I think, examples of using QEEG and normative databases for using neurofeedback as well, like in combination. But I don't think there were any great theories about how all these things might work within, sort of fit within a neuroscience background. And then as I did my PhD in his lab, and I started to look into more of the literature on brain, and also even now we don't really know how the brain actually works, but we do know that some of these signatures of brain disorders have abnormal patterns or measures that we can use these biomarkers to look at. And it's more and more apparent that some of these functional signatures of brain networks as well as oscillations are linked to function and dysfunction. So, and then of course I also, because of my physics background, I started to look at also some of the new theories about the brain in terms of this theory about entropy and order disorder and sort of basically synchronization and desynchronization. And also this theory called self-organized criticality that seems to explain a lot of the reasons why maybe the brain is looking for kind of a middle ground in terms of all these patterns, which I'll get to more during the course. But I think there is potentially something there that one could have a general theory of how neurofeedback might work, at least 𝗔 neurofeedback. Then of course there's other types of neurofeedback, but at least from the point of view of 𝗔, there's more and more evidence now linking 𝗔 to behavior and how it's maybe linked to kind of abnormal brain states. So, for example, we know that during epilepsy, for example, there's very hypersynchronous states and you lose consciousness. And that may be related to very limited number of states that the brain can visit. So very repetitive kind of patterns or, highly synchronous activities that stop information processing from happening in the brain. And then conversely, you have also other states like psychedelic states that have less synchronization that are linked with kind of brain dysfunction. And then, of course, different networks like the fault mode network, different networks that are related to specific functions in the brain, like self-referential processing, like memory or working memory and so on. And it seems like in some diseases, these networks are selectively affected. And some of these networks also have kind of a different sort of brain rhythms that are linked to them from the neuroscience literature. So there are some, EEG fMRI studies that have linked particular EEG activities to fMRI networks that we know have particular functions and so on. So I think all these things, you put them all together and you try to connect the dots a bit, you can have a little bit more of a reference of how, you know, these oscillations are linked to functions and where they occur also anatomically in the brain, and so on and so forth. Yeah.
Thank you. And I recently learned that you'd spent some time in London, Ontario, at the University of Western Ontario, and I learned that the origin, I wonder if you could talk about this, that it was actually at a trauma conference. You were introduced to Dr. Ruth Lanius, and that began the relationship where you kind of helped to show her the, you know, what you had been studying around EEG biofeedback and so on. Can you talk a little bit about that?
Yeah, I can share an interesting anecdote actually. So the person who recommended me as a postdoc to Professor Lanius was John Griselli, because he met her at the trauma conference actually. So I wasn't there directly, but he said, "Oh, I had just a PhD student who just got his PhD and he's looking for a postdoc," and he sort of recommended me. And then I met Ruth, and she was very interested to use neurofeedback sort of in her practice as well as in her research, because by that time she was mainly doing like fMRI and neuroimaging research in PTSD, and I think they were doing a lot of psychotherapy, and she has more like a mind-body approach to treatment. But she was looking at, you know, she got interested, I think, through 𝗬𝗏 and neurofeedback. And at that time, I was kind of floating around looking for a job. And then she invited me to come as a postdoc to London, Ontario. And I actually had finished my PhD. And during that time, we were looking at, I was looking at some approaches to surgeons to improve their attention. And I was actually involved with some research on meditation and looking at like how to enhance kind of attentive states during meditation. And so we started off with this study looking at how alpha is linked to attention. And the idea was to, improve attention with neurofeedback based on alpha rhythms, because alpha rhythms are linked to attention, so attentional states. The fact that the alpha rhythm usually decreases, it's kind of like a gate that sort of blocks sensory information from the outside. So to reduce the alpha means kind of opening a gate. It means it's kind of a proxy for the person being attentive to external stimuli. And so that's what I learned from my PhD. And then we applied this protocol directly in some healthy subjects. And we found that actually decreasing these rhythms could improve their attention, or at least decrease their mind wandering. And as you know, like mind wandering kind of is task unrelated thoughts that are actually generally implicated in psychiatric disorders. And so in depression and PTSD as well, people have a lot of mind wandering, sort of intrusive thoughts and thoughts that are negative and so on. So the idea was, okay, to apply this protocol, also to translate this protocol that we saw that was promising to PTSD patients, but it turned out to be much more complicated than that. So I will leave that to the course to explain a little bit how these things are related. But it turned out that actually increasing alpha rhythms were better in PTSD rather than decreasing them. So there's a lot of paradoxes in the brain, but it does make sense from this point of view of trying to find the middle ground, the kind of middle excitation inhibition balance, as well as the internal and external trade-off between internal and external processing in the brain. So it seems like, yeah, that also led to, I would say, an accidental discovery that this protocol that we have recently shown that improves PTSD symptoms can also be found by decreasing alpha rather than increasing alpha, which was like the Pen-Skill-Kolkovsky approach, the classic approach. So it's interesting to see also from the point of view of neuroscience why both protocols might work and have efficacy, even though they one protocol, the Pen-Skill-Kolkovsky, increases alpha, and the protocol we worked with in Ruth decreases alpha, but they both seem to have beneficial effects. Yes.
Thank you. A lot of the folks who are likely to be interested in this course approach neurofeedback very much from a mental health perspective of wanting to help people to find a better way to function in their lives, to heal, etc. I wonder, and one of the questions that comes up a lot is like, what does neuroscience have to offer So I guess that's a question that I'm asking
Yeah.
you. Is what would neuroscience have to say that would help somebody who is a therapist, for example, understand, be able to explain to a patient how neurofeedback works, or what it does, or why it does what it does?
Yeah, I think from the point of view of trained therapists, I think you can explain a lot of things. To the patient, I mean, we try to simplify things and get them to understand a little bit how things work. And maybe if you have enough time to explain it, although it's complicated, I spent my whole lifetime trying to work out a little bit, the last academic lifetime, I mean, to work out how neurofeedback works, but it's very difficult to explain it to sort of lay people because the brain is so complex and there's so many different aspects to information processing in the brain and so on. But at least during a course that is over these 8 hours, I think you can lay the foundation of how these things are connected. It's important to know because essentially when you're looking at simply the mental health point of view or the behavioral point of view, if somebody's saying, oh, I feel sick, or I don't feel well, or I have a cognitive dysfunction, so on the surface, all these things may appear similar. So, when somebody comes out, I'm depressed, well, they might have the same diagnosis, but their brains might actually be different. So the circuits implicated might be different. So it's a little bit like opening up the hood of a car and finding out what's going on, which bits are connected to what, and how to fix it. So it allows us to look more at the mechanics of the problem and see where we can target. Without which, if you just look externally at a car, you would just say, oh, it can't drive, or it seems to have these and these symptoms, but you don't really know what's the underlying causes. So in some sense, neuroscience opens up the hood and you can see these circuits, or at least you can use some of these methods like EEG and QEEG to ascertain, which parts of this system may be broken, or maybe should be used as targets for recovery. And then also you can use it prognostically. So in the sense is, if you are fixing something and the person is feeling better or not, you can then track these targets and see, okay, are they also moving in the right direction or not? Are they, are you restoring some of these activities that you're targeting, or are there no changes, and so on? So you can use it as like a prognostic sort of measure of treatment. And then you will also know, okay, at what point do you stop a treatment? Or maybe if you have several candidates that are maybe, potential for treatment, you might, change to another candidate because one of these candidates was not a really causal candidate. So there's a lot of, for example, what I mean by candidate is like, let's say you find multiple abnormalities in a QEEG. You won't really know which one is the one. Usually you go with the one that's maximally deviant, but that might not be the one that's causally related, simply because correlation is not causation. So you really need to intervene to find out. But then if you don't find out that the treatment doesn't really affect the symptoms of interest, then you might try to change the measure that you're targeting. And so basically it gives you, and essentially it boils down to the very basic fact is that with neurofeedback, you are targeting neural features, right? You're not targeting behavior. So you need to know what these neural features represent, or how they're linked to behavior to kind of make sense of it all. So if you're using another behavioral intervention for mental health, then it's a different matter. Then you don't really need to know about the brain in some sense, apart from maybe like learning and conditioning and so on. But if you're using neurofeedback and you're using neural signals to train somebody, then it's important to know what these neural signals represent and how they're related to behavior.
Thank you. So for folks who are working in the neurofeedback field, it's easy to forget that that for most of the world, there is not a sense that we live, that the human body, that the nervous system is neuroplastic, that there is this oscillatory sort of electrical activity that really plays a large role in how things work. What I wonder is, in the field of neuroscience, would you say that is more widely understood as an underlying function of how things work, or has there been a change in that over the last, say, 10 or 20 years in your sense?
Yeah, I would like to think that neuroscience is much more aware of the potential of neuroplasticity, right? And there's been a lot of studies dating back 50 years that have shown, and the whole point of the neural system is that it can learn and can change So it's kind of neuroplastic by excellence, even more maybe than muscles and so on. But I think it's underappreciated with the current models of treatment that people use, especially like medication. Because with medication, you're sort of saying, oh, you have this kind of lack of something or too much of something, so we will then titrate it and we will, apply it from externally, and then we will supplement that. And then you will be again restored to the proper balance, and that's kind of inherent in these antidepressants, for example, where the model is that there's a lack of serotonin, and then with the antidepressant you kind of boost the serotonin levels, and then you will be optimal after that. So there's very little narrative, at least in the kind of biomedical model of mental health so far, that plasticity really is powerful. Even though neuroscience, there's multiple examples of neuroscience showing that things are very plastic in the brain. Going back to the recent, craze about meditation that shows structural changes in the brain after, behavioral sort of repetition of particular mental states, or even when you're learning particular motor tasks or any skills, it's clear that, neuroimaging has shown, I think basically the evidence is actually cannot be challenged anymore. So there's a lot of evidence, but the problem is that the treatments that people use are not really based on plasticity, as far as I can see. I mean, maybe brain stimulation can be seen as a little bit like that. They talk about plasticity when they say, okay, we stimulate the brain, so we're going to now change the plasticity circuits. Although there's some inherent problems with brain stimulation to induce long-term plasticity. So essentially, I think neurofeedback has a unique place there, because they can target neural measures, and the targeting of those neural measures can be seen as a long-term plasticity, compared to very many of the other techniques that do not show evidence of long-term plasticity. What I mean by long-term plasticity is essentially once you stop a treatment, you don't need to apply further treatment. So with brain stimulation, you can apply the treatment, there's an effect, but if you wait a week or a month, usually these symptoms return unless you provide further stimulation. Whereas with neurofeedback, there's multiple papers showing that these the effects can last years, months, if not years. So it's a radically different way of showing that plasticity is really durable, and it can be lasting in some sense, right? That you can rewire the brain almost permanently in some direction, and then it can kind of stay there, hopefully. So I think it's still underappreciated in neuroscience, let's say in the mainstream neuroscience, and that's why the uptake of neurofeedback has been so slow, I think, as a treatment. In general, interest by the community, obviously scientific community, is better than before, but it's only like maybe a fifth of what brain stimulation gets these days. So there's a lot more progress to be made, at least to make scientists investigate its effects even further. Yeah,
it's interesting. Thank you. One of the things that really speaks to me about neurofeedback is that it's kind of an empowerment model. It puts the locus of change, the learning, on the person who's coming in for neurofeedback. It says, you have the power to make these changes and to learn a better way of brain function. And I wonder, from a neuroscience perspective, is there evidence that, as opposed to the medical model where you're going to come in and the doctor is going to give you something to make you better, the idea that the clinician is actually empowering the client to learn a better brain function. Is that, from a neuroscience perspective, is that a sort of accurate way of looking at it, in your view, or is there some neuroscience around that? Yeah,
I think in general, obviously any treatment that you can seem like you're in charge is going to have a psychologically beneficial effect on you, because you can dictate also how much you want to partake in it, and if you don't want to, you don't have to, and so on. But actually, from the point of view of there's different models of how neurofeedback might work. In some models they say, well, you're learning a skill to regulate, and I'm not completely thinking that that's an incorrect model. I think, of course, you're learning how to regulate, but I think in many cases you're also changing kind of the baseline state of your brain. So because of this plasticity, so it's a little bit like also like, let's say, training your muscles in the gym. Of course, it's better if you go to the gym yourself and train your muscles. And why is that better than just receiving electrical stimulation on your muscle? Well, eventually, maybe the outcome is the same. If you stimulate electrically the muscles, it will give you the same strength as if you do it yourself. But the difference is that if the system itself does the work, then the signaling and the messaging that creates those changes come internally from the system, because it's a closed system. So these changes that you create on your own are actually more stable because the system itself homeostatically has created it. But if these changes are induced from the outside, then the system actually fights those changes, because the signal doesn't come from the inside of the system. And therefore, these changes will drop off very quickly if they're done from the outside. So from the point of view of neuroscience, that's really the difference. It's not so much as you learning a skill where you feel better because you're doing it yourself, but it's more where the signaling, where these triggers for change come from. And so because if you consider an organic system like the human body and the brain to be a closed system, then all these things are in balance because everything is coming from the driver. Whereas if you're being kind of controlled from the outside, then the system is actually reacting homeostatically in the opposite direction. And that's why, for example, I mean, it's a long topic that we will discuss in the course,
Sure.
But essentially that is basically why giving medication, for example, will never have the ultimate effect in the direction of treatment, of hoped treatment, because the brain is reacting homeostatically in the opposite direction. So in fact, you have these mirror image effects. For example, you have also increased tolerance. That means you have to increase the treatment with time, which doesn't happen with neurofeedback, for example. So if you know something works like a drug, well, why do you need to then increase the dose every time? That's because the system is becoming less sensitive. It's habituating to the effect, and that's because the thing is being driven from the outside. And then even more, worrying is that once you completely remove the treatment, then you have withdrawal, which means the symptoms almost return immediately, and they're even sometimes stronger than before, because again, the system is adapted to this external stimulation. So essentially, that's why it's better, in my opinion, that these things are done from the inside. And I think some of the papers show that that's why the effects of neurofeedback are more robust in the long term. Yeah,
that's great. Thank you for clarifying that for me. I have a couple of other questions, and then I was thinking that we could open it up in case there are folks who are attending now that also have questions they want to ask you. We were talking sort of generally about, it seemed like we were touching on the idea of what the model for how neurofeedback is working. And I know for as long as I've been doing this work, the sort of go-to model for most people is that it's operant conditioning. And I know that there are a number of other ideas for how to look at what neurofeedback is actually doing that have become more popular in recent times. And I wonder if you could talk about some of the different ideas. I think what you're just referencing there is a homeostatic model of how things are going. I wonder if there are some other ones.
Yeah, exactly. The operant conditioning is the classic model that came from behaviorist theory, and behaviorist theory didn't care about what is the actual framework in the brain. They kind of completely ignored cognitive cognition in the first place, plus even internal states, or let alone neuroscience in general. So it was a very superficial way to explain how things are related on the surface, just from the behavioral point of view. But we know, of course, that the brain is a biological system. It has its own rules. It basically follows very similar biomedical rules as any other organ, right? If your nerve cells get sick, then something is going to happen that isn't great. You have a stroke in a particular area of the brain. Well, that's because the nerve cells are not working there properly. And you know how particular areas of the brain, especially sensory areas, can easily predict, where the problem in the sensory processing is. If you have a stroke in the motor cortex, well, you will have a problem with motor movement and so on. So these are things that behaviorist theory can never explain in some sense from the point of view. But since we've mapped these regions and these biological anatomical areas, we know how these things are related. A little bit like we know how a machine in a car is related to the function of particular parts of the car, of the movement of the car. So, but essentially there are multiple models, and I don't think this more modern neuroscientific model that I'm sort of pushing a little bit for people to try to understand is it's not necessarily exclusive, or it doesn't exclude the point of view that operant conditioning is a valid model. Operant conditioning is a valid model because it says that if you train something in a particular direction, it will kind of promote itself in that direction, right? This skill. But it doesn't really explain why it lasts long term, and even operant conditioning in general. Yes, you learn a skill, but where is this skill sort of, coded, or where is it really stored in the brain? And we know that it's stored in the synaptic connections. So in some sense, it transfers the locus of you learning a particular skill, which is kind of in the brain somewhere or in your body. You've just learned the skill into somewhere in the system of how the neurons are connected. Now, of course, a particular skill like driving is much more subtle, and that's distributed over many different systems in the brain, because you need motor, vision, and so on. And so you learn these things, like a normal skill that we use, that we call skills of normal life. But a particular skill like changing a particular brainwave pattern is even more, let's say, basic, and changing that brainwave pattern into something more lasting is, let's say, even more basic on the levels of the neurons that generate those patterns. So what I'm trying to say is that the patterns of, for example, what the brain generates to create a very complex skill like driving is actually much more complex than simple patterns like alpha oscillations or particular epileptic states or different things, how things are connected in general. So we're not really looking at skills that we call in daily skills, but we're looking at, okay, how these neural populations generate particular patterns that may then impact a lot of other functions. And then those functions will obviously create cognitive dysfunction and so on. So if you then, so you're going more like low level. And so the low level is how the neurons are connected, and this is how they generate these oscillations. And so if you modify these oscillations at the low level, or the neurons, how they're connected at the low levels, then they have an impact on the upper levels, which are like skills like cognition and concentration and attention, and so on, and also affective processing and so on. So in fact, you're taking a much more reduced approach to brain disease, and you're simplifying it to say, actually, it's a very simple thing where how things are connected, and then those are things that then impact these more complex functions that we know that are more human-like. But without that connection, if these lower levels are not working properly, just like in stroke, you just sort of turn off a particular region, well, you have very, big impact on behavior. But actually, the lesion is a very simple thing anatomically. You can see it on an MRI scan. It's not rocket science, right? So that's a little bit like how I like to see with neurofeedback. And so this homeostatic model is an addition on top, and how these neurons are seeking, let's say, at the middle levels of activity, how they're tuned to have the optimal balance between excitation and inhibition and so on, and then how this is reflected in the brainwave patterns and so on. But I mean, in general, I think there is a new framework there that's potentially useful, where people can see, apart from behaviorism, learning new patterns, how these patterns can be then imprinted in the brain using neuroplasticity. So I think operant conditioning doesn't really explain neuroplasticity per se. And so therefore we need neuroscience to explain a little bit like why are these lasting effects imprinted in neurons, right? And then different types of plasticity. So there's two main types, which is the Hebbian one, which is more correlative, and then there's a homeostatic one, which is kind of a negative feedback loop. So we will cover those two types of plasticity in the course as well, right?
Great. Thank you. And then there's a question about what to me seems like the sort of most miraculous outcome of like this at the heart of neurofeedback is this idea that the brain responds to information. And I've heard it described as the brain just wants to be in control. And I've also heard it described as the brain seeks its best function. And so you're just guiding it towards improving its function. I wonder, does neuroscience have any more insight into what is actually happening there? Why does the reward system that is provided by neurofeedback work?
Yeah, I think the magic of neurofeedback is the actual knowledge that you're feeding back.
Getting a little bit of delay. I don't know if that's, or other folks seeing a delay as well. Okay. Do you want to try again, Dr. Ross? Let's see, maybe it's gotten better. It's a little bit like when the person who's doing the prize, the award thing goes, and the winner is, the transmission cuts out.
I think I've apparently muted myself, but I don't see that I've muted myself. Can you hear me now a bit better?
Yeah.
Yeah.
Interesting.
Okay. Is it better now?
Well, we hear you, but your vision, well, yeah, it's coming and going.
Is it better? It's coming on slowly. Should be okay now, no?
Yeah, maybe try and we'll see.
Yeah, so what I was saying is that it's not magic that the neurofeedback works, because basically the information you're providing is through the feedback. So the feedback is critical to be able to tell the brain which direction to move towards, right? So it's a little bit like when you're playing the game hot and cold and you want to find an object and you're telling the person, okay, you're hot, 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 you're close to this object, or you're cold, cold, cold. That's kind of feedback, right? And that guides the person to find the object they're looking for. And so it's the same when you're feedback. If you want to modify a particular brain pattern, you're telling the brain, okay, you're closer and closer to this signature that we want to promote, or you're further and further away from this other signature that we don't want to promote. And so that information the brain is using. It's a little bit like, you know, if I blindfold you and you try to find your way, you need some guidance to get to where you want to get to, right? And so the target is basically set by the neurofeedback, and then the feedback is the thing that's allowing you to get to that target. Now, without that information, the brain cannot really move all the way. And so it's working in a closed loop, which is kind of considered as operant conditioning. But it's everything that you learn is based on feedback. It's based on a neurofeedback, on a feedback loop, where you get trial and error, and you get negative feedback for making errors, and positive feedback for moving in the right direction. So it's not a magic principle. It's just applied to brain signals. But in general, feedback is used in anything you learn in daily life, right? From walking to talking to anything that you're doing, you have some kind of feedback about what's happening around you, right? It's just that we take it for granted that feedback is a special thing. But actually, without that closed loop, there's no way you can learn anything.
Yeah, great, thank you. And the sound seems to be coming through fine, and we're just getting sort of staccato images of of you. And
at least the sound, yeah.
Which is fun. The sound makes it understandable. I wonder if there are any questions from folks who are joining us. Then you please feel free to either post it in the chat, or I see Henry, you sound like you have a question. Would you like to go ahead?
Yeah, sure, I would. The one thing that really has always confused me about neurofeedback is, how do you know what signals you're getting? You're on the.
Oh, you just muted.
Yeah, it just broke up on my end as well. So
yeah, we heard
how
do you know what signals you're getting, and then you stopped.
Can you hear me now?
Yes.
Yes.
Okay. The thing that's always driven me nuts is the placement of electrodes, because you're not really sure what you're getting there. What signal is it coming from? That area of the cortex, or is it coming from deeper in? Is it all the way down to the brainstem? You know, you hear all these theories and why various protocols work, and then you look at enough, images of brains that are, from X-rays and so forth, and yeah, they don't correspond at all to drawings of the brain, and they're not symmetrical. I mean, I actually saw one where the right hemisphere actually was squished over here. So if you were at IZ, you were actually about 2 inches onto where, say, O1 would be. I mean, it was really a pretty bizarre brain, but all heads are shaped differently. Are we really that conformed to? And so then you have the hair problem. I mean, good luck getting the same spot on the electrode with a bushy head. It just isn't going to happen. And those helmets are, so that's my question. What are you really getting, or does it matter?
Yeah, that's an interesting question. I would say, there's probably a trade-off between what can be very accurate and not accurate, in the sense of we will never reach complete accuracy with EEG, let's be honest. I mean, it's very blurred signal, and there's different ways of making it more or less accurate, like, for example, inverse source localization and so on. And so at the moment, like, neurofeedback is, in some sense, if you're doing it with one electrode, let's say it's firstly in a very basic state that needs to be innovated. And maybe with more electrodes and dry electrodes and so on, we can make this more accurate. But even so, even if you're saying, okay, how come even one electrode neurofeedback works? And, there's some of our studies are based on one electrode neurofeedback. And essentially, the reason why it works is that actually in this case, the localization isn't that critical. And so you could think about that the global brain activity, or even maybe, activity that's coming from one big lobe, let's say parietal lobe, is good enough to tell you that there's an imbalance in these neuronal populations. So even an EEG signal that you record for one electrode is spread over maybe 5 centimeters squared of actual cortical patch. So you're not going to be obviously capturing anything directly of any subcortical activities, but you are capturing firstly cortical activities, and let's say a 5 centimeter square patch, and that patch is already telling you that the brain, if you're looking at the activities versus some kind of normative group, is telling you that that patch is actually quite abnormal. And so, for example, in PTSD, alpha, which seems like a very general way, that was discovered almost 100 years ago, is enough to actually classify PTSD quite well, to up to something like 70-75%. So 3 out of 4 people with PTSD have this abnormality. So in some cases, you might need very specific biomarkers to try to work out the personal situation of the person in terms of their brain health. But in other cases, there might be some general markers that actually apply to within a disorder to a lot of people. And then if they do display this marker, then it might be a starting point to help them with treatment. Like, for example, the alpha wave seems to be linked to this excitation inhibition balance, and that's linked to arousal, and arousal then linked to sleep and so on, and hyperarousal and hypervigilance. So basically, this very basic axis is enough to maybe help them with these kind of symptoms. Obviously, it's not going to address the trauma itself, but it's a starting point to help them address, the very strong symptoms that they have of hyperarousal. So in many cases, the anatomical specificity of the biomarker is not necessarily critical, because it is a global biomarker that is generally telling you the state of the central nervous system, irrespective of the location on the brain. And of course, EEG is mostly cortex, and even cortex, you could say, well, it's just, like the upper sheath of the brain. How come we can't see all the other things that are very important? But the cortex is kind of like the top of the pond, like it also reflects what's happening underneath. And because the system is talking to, there are also loops with the thalamus and so on, the cortex still, cannot betray its imbalance in general. So you see a lot of things through the cortex that you would not maybe necessarily think you can, but obviously it's not the full picture.
Okay, thank you.
Hopefully that explains things, yeah.
A little bit, yeah.
Any other questions?
We have one from Leanne in the chat.
Sure. Leanne, do you want to ask it, or would you like Kieran to go ahead and ask it?
I'm happy to ask it if that is good for you.
That's great.
Hi. So my question, and this might be better fully addressed in the course, but I thought I'd just pose it as so many emerging technologies are coming out with neurofeedback. I mean, I can count probably a dozen ways to do neurofeedback at this point, plus probably a few more of how to read QEEGs. And I think a lot of us exist at this intersection of wanting to figure out how to best help our clients. And I was just curious with the emerging research, if things are coming out about different ways and being more effective for certain disorders, or show more efficacy in the research. Obviously, I'm very familiar with Ruth's work with alpha down, which is a unique amplitude training.
Yeah, I think we're still early days. I mean, I think as neuroscience develops, and especially neuroscience of EEG develops further, and this is unfortunately an underfunded area. EEG has been mainly used for epilepsy, like research and in hospitals, right? So it's been completely ignored by psychiatry for, let's say, 50 years, I would say. And only just now, in the last 5 years, people have been talking about EEG biomarkers, right, for psychiatric illness. Now, for neurological illness, yes, for epilepsy, there's such a thing. But even there, in epilepsy, they just look at the visually, they just look at spikes. Okay, you have a spike, you have an epilepsy, you don't have a spike, and they localize the focus and so on. But they don't take into account what current research has been showing, that in fact, in a lot of cases, you can actually detect epilepsy or epileptic signatures of epileptic brains from the interictal activity, which is kind of like the background activity of the EEG. And so that's where the Q of the QEEG comes from, right? And, there's been a lot of proponents of QEEG, from Leroy John to Robert Thatch and so on, that, came up with this terminology and that goes hand in hand with neurofeedback. But these are still ideas that, let's say, neuroscience, is slowly embracing, but there's more and more evidence that they're becoming useful. And especially within the framework of machine learning, people have started to apply machine learning now based on EEG data and trying to see, okay, which of these measures or biomarkers, which we can get into, might be discriminative of different diagnoses, different cognitive states, behavioral states, and so on. So there's much more to be done, but I think there is emerging research that shows that, you could use EEG promisingly as a non-invasive method, as a cheap method, as a method you can use in the clinic, that kind of also a little bit, validates these previous approaches from the, back in the 1980s that came out with the normative databases. Even normative modeling is now a hot topic in psychiatry, where, normative modeling actually in psychiatry started from, based on MRI data, like structural MRI data, and it showed normative model changing across age and so on, and showing that in schizophrenia, every schizophrenic brain is different and so on and so forth, and that we should use normative modeling to not assume that every schizophrenic brain is the same and so on. So, and then it's moved to functional MRI, and now we're finally onto EEG, and actually I'm working with a group in Tübingen, we're creating the new models for normative modeling of the EEG based on more electrodes. But of course, this is not a new idea. It's back from the 1980s, from Leroy John, published in Science. So essentially, I think there is more and more, data out there that implicates particular functional measures. And we're not just talking about amplitude. We can talk about different measures like 1/f, connectivity, things that have been around for a while, as well as new things that are new markers that probably will have, databases that will be, assessing these measures across development. And then as more and more of these measures do get detected, then there will be more and more, use of them for them in the clinic. But I think, we can't get ahead of ourselves saying this is going to be a perfect way of categorizing all brain disorders. But this is also not the case with fMRI. So we also have to appreciate that at the moment, neuroscience is limited in being able to also say, well, take two depressives, to the people with depression, why are their signatures different? And can we actually differentiate the two based on their behavior and so on? So this is still, work in progress, but there's definitely clear evidence that we can use neuroscience data to maybe classify particular disorders. And for some disorders, it may be more difficult. And then when we have to go accept these disorders are very heterogeneous, and maybe there's not even a biomedical basis for them. But for some disorders, there might be more, replicable and, robust biomarkers that we can say, okay, if I find a person with this diagnosis that has this measure, and that's backed up by neuroscience data, then we can be more confident that this will be replicable as a treatment as well. So that's the idea, is that, people don't just propose different theories, anecdotally, oh, I found this signature, so this means that, or, so essentially we need to use science to replicate and then see, okay, which things really replicate and which things don't. And that takes a long time, unfortunately, but I think at least we're starting on that journey now in the last 10 years, let's say.
Yeah, and it sounds like from there that kind of not dictates, but would enlighten our treatment approaches. If we know what the sort of biomarker is, then we could pick a modality of neurofeedback that addresses that biomarker. But if we don't have the biomarker piece, we can't pick an appropriate treatment, except every clinician has our favorites that we think work, and we have our subjective idea about that.
Yeah, you can take the empirical approach that you take a QEEG and you look at the most deviant thing, and then without any theory about or any kind of other, background data that this biomarker has been implicated or not, which is basically what's been happening so far. We just work on that, deviation, and we don't ask why and how this is linked, or what papers have found this or didn't find this. But the hope is that using pretty much the same tools now in a bigger clinical setting of, replicable neuroscience with bigger samples of, 100 patients, 200 patients, 1,000 patients of particular diagnoses, that we will be able to tease apart a little bit better. And then from that, but the idea is that to provide kind of a basis for how to be able to interpret this. And then as new data comes in or new papers come out, you can, you have the tools to say, okay, well, it looks like, this biomarker through a meta-analysis or something seems to be linked, right, to this problem. Or maybe there's a new marker that's even more specific. So we don't know yet how specific they're going to be, but it seems okay. Like, for example, our latest machine learning paper, we have 61 patients from the Ruth's lab, and we used alpha to classify in this other framework called microstates that we can maybe also learn in the course. So there's new frameworks coming out, and maybe in the future they will be all based on Loretta and who knows what, and then we'll have to use a combination of different things. But with the fact that you increase the let's say the palette of different markers, and if you think maybe in the past it's always been just about power and I don't know, connectivity, and now there's many different connectivity measures. There's also in source space, there's also microstates. There could be other things on the radar in a few years. You can look at even raw data, deep learning, who knows. But if you are able to identify the biomarker, even though you don't know why that biomarker might be useful, you can still feed it to the neurofeedback. So even a multivariate biomarker that has multiple, measures inside, like let's say a deep learning classifier, you could technically use that for neurofeedback, even though you don't know what it represents functionally, as long as it's actually accurate to detect the brain state, right? So you could take a simple classifying the disease problem, which seems to reach a plateau of maybe 80% classification. So we're not definitely there 100%. But you could say that maybe 80% of the time your patients did good work. Or you could also say within one patient, we can get to this in the course, but there's another approach where it completely turns this approach on the head, and you say personalized medicine, and you don't say, I don't care what all the other patients look like. All I care about is how this patient is related to their symptoms and how their EEG patterns are related to their symptoms within patient, right? So for example, in the future, you can imagine maybe somebody would wear a portable EEG hat at home, and you would ping them every so often and say, okay, how do you feel at this moment? Or when you feel your symptoms, you would put on a cap, record the EEG activity, and then when you feel better, you would put on a cap and see what the activity looks like with those times. And then the classifier would classify within subject the sort of bad states or the bad signatures and the good signatures, and then you could use a neurofeedback protocol based on the patient-specific signatures based on the symptoms. So there's a lot of different ways of approaching the problem that doesn't necessarily involve normative databases, right? And this is what's been done actually recently in one Nature paper. They had an N=1 paper, so only one patient, but they had deep brain electrodes implanted, and they were tracking this subject, through the internet, and they were feeding the data, getting the data, continuously as a stream of kind of LFP data, but it's kind of like EEG within the brain. And then they were looking at, okay, when the person said, I'm feeling very like obsessive compulsive symptoms are high or depression is high, then they would see during the EEG, basically the brain signals, how the patterns look like. And then they actually found that it was gamma activity in the amygdala that was the most discriminative feature, that was, discriminative of their symptoms of depression. And then they fed back a kind of deep brain stimulation based on the gamma and the amygdala. So you can imagine maybe translating that approach non-invasively to EEG, and then instead of using deep brain stimulation, using neurofeedback, right? Don't know if that makes sense. So there's different ways of maybe, simplifying, maybe further, becoming less invasive. But of course, we need to find out whether the limits of EEG can also, be useful there. Because, if you could insert electrodes in the brain, then of course you're going to get more local activity. So the idea is maybe even neuroscience in the future might be able to capture deeper brain regions in some sense. We don't know yet whether there will be technologies, like different things like brain-computer interfaces, which will have neural lace or something like that inside the brain, sensors everywhere or something like that through the bloodstream. I don't know. But it is possible, theoretically, that you could give neurofeedback from any area you wanted to, as long as you have a sensor for it.
Great. Thank you. Julia, you had something you wanted to ask.
Yeah, hi.
Hi.
So I just wonder what might be the practical implications of the course. So my idea is that we can get a deeper understanding about the underlying mechanisms of neuroscience and theoretical models we probably don't know yet. And that these might help us to understand how and why neurofeedback works and how we might apply it to specific patients. So is this what in the end we might get of your course?
Yes, I think the practical
Everything sounds a
implications.
bit complicated, but
Yeah. It is complicated, but I think the practical implications is that you have a foundation of how to interpret some of these. Firstly, you understand why these patterns are different, in patients, and also why the patterns might be related to particular symptoms. Now, we don't know everything about the different patterns. We know, for example, theta in the frontal regions is related to anterior cingulate, and that in the anterior cingulate, there's some conflict monitoring processes going on. And then people could have like obsessive compulsive disorder because of that pattern. And so obviously I can't exhaustively cover all disorders and all patterns that people have found, but we can go through the principal ones, right? In some part of the course. And then when you see some of these patterns, you can say, oh yeah, this looks like a classic pattern of what has been found in the neuroscience literature so far from those, maybe let's say a handful of EEG studies or MEG studies that have looked at EEG in a particular brain disorder. Then of course we can also talk about why, there hasn't been always the same pattern, right? Like, ADHD always was, promising that we have the theta beta pattern, right? Now, that also has been shown not to replicate so well, but there are people still that have theta beta. So why is it that ADHD has also theta beta, but also beta or some alpha pattern and so on? So you understand that the brain can go wrong in many different ways. And it's not about one classic pattern that's important, but, finding the pattern that seems to be specific to that person, and then using QEEG to try to reverse that pattern, and then also applying different protocols. It might not be that you want to just use the Hebbian patterns, like changing, in the direction of training, but you might also use homeostatic mechanisms like for PTSD, where you reduce alpha, because, for example, a patient might not want to close their eyes and relax to increase alpha. So you might have to try the alpha down. So it gives you a little bit more options, maybe in particular disorders, what you could try. But I would say the course will not divert too much from what are the standard recommendations by BCIA, for example. I think these things are kind of compatible with each other. It's just more about understanding the background of why these recommendations fit within the neuroscience model, and also maybe give you the tools that as more research comes out, that you're able to interpret the research or the new meta-analyses that come out and say, okay, well, it looks like there's something there that's more credible, that more replicable, so we will try this in the practice. So I would say it's good to use your own experience in the clinic to help patients and also learn from your experience what worked and what didn't work. But it's also good to use other people's experiences. And of course, in bigger clinical trials, that seems to be the most, let's say, reliable evidence. Now, of course, it needs to be also replicated and so on, but the more times it becomes replicated, the more you can say, this is a surefire way to go, rather than try because somebody else recommended this or that, or I had the experience of doing that. But still, taking into account that, it's still a very embryonic science, right? So there is a science there, and it's still at the beginning, but I think at least that to be able to appreciate that it's important, right? To know, okay, where are the limits and what we know and what we don't know, and then maybe see, is it compatible with your clinical experience as well or not, right? And it might explain some paradoxes, right?
Yeah. So this might, I as far as I understand, it might give us some other ideas or hypotheses about how this special person's brain might work and how we might get it into a better balance. So even by, I have to say, sometimes paradoxical seeming training.
Yeah, changing in the opposite direction. For example, the homeostatic thing is not really well appreciated, I think, in the classic neurofeedback literature. I don't think until we started publishing on this data about the homeostasis, where we go in one direction, you have the opposite effect. That was never documented before. This paper in 2013. So at least that concept, I think, is interesting. It's interesting also point of view of neuroscience, because there are a lot of papers showing homeostasis is very active in the brain. So you understand why that it may be the case, and so on. So yeah, it will give you a better basis of what to expect, and if you don't end up having this the outcome that you want, it might be the opposite, and you can say, oh yeah, maybe because this was related to this. So, but there's still a lot of question marks about whether, I know, for example, also like, how do you apply neurofeedback? How often do you apply it? Do you apply it when the person is conscious or not? And in my opinion, the most important thing is also to give you an idea of what kind of neurofeedback, there's a lot of neurofeedback ideas, like, I don't know, neurooptimal, low energy neurofeedback, different, ideas that I would say like a little bit beyond what the traditional neurofeedback approach is, right? And to be able to also critically assess, are these things actually based on some solid theoretical and empirical evidence? Or is this some kind of, invented stuff that, there's really no supporting evidence for that? So it gives you more a scientific basis for what could really lead to proper effects and not. And I think, until some of these other approaches show real evidence and convincing evidence, mechanistic evidence, right? It's not just a point of saying, okay, well, I applied this protocol and then, we didn't take any brain measures before and after, and I didn't even show you whether this activity changed in the right direction or not, because I was providing your feedback. And so all these pieces of evidence are lacking. And then at the end, they just say, oh, and the patient improved, and we also didn't have a control group, and so on. And then promote this as the next hot thing in your feedback. That to me is not the standard of evidence that's required under scientific, framework. And if we're all working under the scientific framework that we want to make medicine replicable and scientific, then we need really large samples, credibly done research with these quantitative biomarkers before and after and during treatment. And then we can say, here's the big picture, or the complete picture of what's happened during this experiment. And until that, is being done in your feedback, I would be very skeptical about anything being replicated, unfortunately. Yeah.
That's great.
Okay.
Thank you so much for all the questions. Thanks everyone for participating today. And Dr. Ross, we will see you in September.
My pleasure. Thanks.
Okay.
It's been a pleasure talking to you. And yeah, I hope to catch you at the course, and we can talk about these things in more detail, obviously, in more concrete detail.
Thank you, everyone.